Let's get going. So today we are going to be covering homeomorphisms, and today is going to be mostly a bunch of looking at examples, trying to establish intuition for these things. We only have one theorem that we're going to prove all today, and it's really simple. So it's mostly just trying to establish your intuition for what these things are. Now, intuitively, what is a homeomorphism? It is a way of saying that two topologies are equivalent. So a homeomorphism is a function from one topology to another topology, but that maintains topological structure. And so in some sense, the two topologies are the same. So homeomorphisms are to topology what congruences are to geometry. When we say that two triangles are congruent, we don't mean that they're identical. We mean that they have the exact same geometric properties. Make sense? They could be in different positions in space. If I have one triangle here, one triangle here, you say, who cares? They can still be congruent because your position in space isn't a geometric property of those triangles, right? Their geometric properties are the length of the sides of the triangle and their angles. Those are their geometric properties. So similarly, homeomorphisms, they don't say that two topologies are the same. They're not identical, but they have the same topological properties. Now, we haven't talked much about topological properties yet. We've only covered one so far in this class, which is Hausdorff. That's a topological property. So any topologies that are homeomorphic to each other are going to have the exact same topological properties. Okay? That's high level, what we're going to be talking about, and you'll notice that we use the exact same symbol for saying two topologies are homeomorphic that we use for saying two shapes in geometry are congruent. Very common notation for saying two things are somehow the same, yet not identical. So let's get started with the actual exact definition of a homeomorphism and what it means for two topologies to be homeomorphic. So let X and Y be topological spaces, so they have some associated topology that we're not going to bother mentioning. And let F, this is going to be our homeomorphism, let F be a function or a map from X to Y such that F is a bijection. Remember what a bijection is?
It's at least 1 to 1
1 to 1
and on 2.
It's 1 to 1 and on 2,
Yeah.
right? By, both. Has both the properties that we care about with functions. Do you remember what 1 to 1 means?
Yes.
Do you remember what on 2 means? On 2 means it uses up this entire space.
Okay.
Yeah, right.
Right?
Yeah.
Okay, so that's 1 to 1 and on 2. So we have F is a map from X to Y, and it's a bijection. Okay. Then F is a homeomorphism provided that both F and its inverse are continuous. Now, do you remember what it means for a function to be continuous?
In topology terms?
Yeah, I don't want you to tell me that for every epsilon there exists a delta such that
All
if x is within delta of x naught, then f of x is within
It's something to do with
pre-images of open sets being open. Something to do with that. Probably that exact thing, right? A function is continuous if the pre-image of open sets are open. Do you remember how we check that? We look at every open set in Y, and then look at its pre-image under the function f. If its pre-image was open, are we all comfortable with the notation, or with the verbiage of pre-image?
Yes.
Yeah.
Okay. So we've got some open set in Y. We've got Y over here, and we've got X over here. We pick an F maps this way, right? Take any random open set here, and look at its pre-image under the function f. If its pre-image over here was also open, then the function's continuous. If for every open set here, its pre-image is open here, the function is continuous. Now, if we're saying that f inverse is continuous, f inverse is a function like this, right? So f inverse being continuous is the same thing as saying that not only is the pre-image of open sets open, but the image of open sets is also open. That's another way to think about it. Instead of having to think about the pre-image of the image.
Interesting.
So it maps open sets to open sets, and it maps two open sets from open sets. Both ways. Some intuition that we typically use for a homeomorphism is it's a bijection between points, and it's a bijection between open sets. Map every open set to one and only one open set. And we use all the open sets over here and all the open sets over here. That's some of the intuition we usually keep in our heads to remember, in short, what exactly it is. So back to the definition. Let's just restart. Let x and y be topological spaces. Let f from x to y such that f is a bijection. Then f is a homeomorphism provided that both f and f inverse are contiguous. Okay, so that's a homeomorphism, but what does it mean for two topologies to be homeomorphic? If there exists a homeomorphism between two topologies x and y, then we say x is homeomorphic to y, and we denote that x is homeomorphic to y. Not every function from x to y is a homeomorphism. We're saying if there exists at least one function from x to y that's a homeomorphism, then these two are homeomorphic. Does that make sense?
So you're saying there could be more functions that exist between these two that are not homeomorphic?
That are not homeomorphisms. The functions are homeomorphisms or not homeomorphisms. The topologies are homeomorphic or not homeomorphic. So yes, it is
There can only be
possible
one or
for
the
me to
other.
have a function from x to y that is not a homeomorphism. There's tons of ways I can do that. I can map every point in here to just one point in there. Not a homeomorphism.
But if there exists one where these two are homeomorphisms, then the whole thing is homeomorphic?
Right. So how do I prove that x is homeomorphic to y? I need to find some function from x to y that's a homeomorphism. If I can find some function that does it, then they're homeomorphic.
Okay.
Proving that they're not homeomorphic is harder. How do I prove that there are no possible functions that you can get from x to y that are homeomorphisms? That one's a bit more trickier, and we'll rehab that conversation at the very end of the lecture. But in showing that they're homeomorphic, that one's more straightforward. We just need to find one function from x to y that's a homeomorphism, and we're done. They're homeomorphic. That makes sense? Okay. Intuition, we already said that. So let's get to examples of these things and get to as straightforward an example as we can. Let x be the set A, B, C. Let y be the set 1, 2, 3 with these topologies. Here's x's topology, here's y's topology. Now notice those topologies have the exact same structure. Now what's the map that makes sure you preserve that structure? Well, there's a bunch of them, but here's one. If we map A to 1, B to 2, and C to 3, then after our mapping, well, then you can see, obviously we're going to map this open set to this open set, this open set to this open set, this open set to this open set, and this open set from this open set. You see that? So here's an example of two homeomorphic topologies, and here is the homeomorphism that proves that they're homeomorphic. And we,
Technically, so could you just have A to 1 and that would prove that they're both homeomorphic? Because you only need one example of it, or do you need all of it to be?
I need a function from x to y.
Okay.
If it's a function from x to y, it has to map everything in x to something in y. Furthermore, it has to be a bijection, so I have to map everything in x to everything in y.
Okay.
Notice that x and y have to have the same cardinality. Size. If I create a bijection if I map everything in one set to one and only one thing in another set, then those two sets have to be the same size. That's how we actually define two sets being the same size, is if you can create a bijection between the sets, then they're the same size. That's called an isomorphism for sets. It's the most basic way you can say sets are somehow the same. They have the same size, a bijection. So now we're using that bijection again, so we're saying not only are the sets the same, but the structure on those sets is somehow the same as well. And hopefully it makes perfect sense that F is a homeomorphism, right? Obviously it's one-to-one and on-two, so it's a bijection. Obviously it maps open sets to open sets, and obviously the preimages of open sets are open sets. We need all those things. It's got to be one-to-one, got to be on-two. It's got to map open sets to open sets, and it's got to have preimage of open sets or open sets, because we need F and F inverse to both be continuous. Make sense? Okay. Let's look at another example. So notice now, we're going to take X, and we're just going to give it two different topologies. Don't get confused. Here's one topology on X, here's another topology on X. I can call this topology over here, to help me clear, we'll call it tau 1, and over here we call it tau 2. And what am I proving? If we're being very explicit, I'm proving this topological space is homeomorphic to this topological space. It's still two different topological spaces, they just happen to be defined on the same set. You with me? There's an infinite number of topologies we can define on one set. Well, maybe not, depending on the set. But the real numbers, we've talked about a few different topologies on the real numbers. We talked about the standard topology, we talked about the lower limit topology, we talked about the finite complement topology, the one that always throws you through a loop. So I was always on the real numbers, but we had a bunch of different topologies. Similarly, here's some set, here's two different topologies on the set. They're both topologies, they're perfectly valid topologies. We're going to prove that these two topologies are somehow the same. And hopefully from the picture, it's obvious how they're somehow the same, and you can see that they have the same topological structure. So let's find the homeomorphism that proves it. Well, obviously we just mapped A to C, B can go to itself, and then C to A. That gets us from here to here, keeping the exact same structure. Is there anything weird about that? Let's make sure that these make perfect sense, because this is as straightforward a picture as we're going to get. It's going to get a lot more high level after this. So if there's anything weird here, anything that needs clarification, let's clarify it now. There's a discrete set with 3 points is nice and simple. Nothing? We got it?
I think so, but
All right, let's move on. Okay, so let's look a little bit more high level now. Let's look at a function from the real numbers to the real numbers. The real numbers with the standard topology. So this has standard topology, this has standard topology. And we're looking at a regular function that you're used to seeing all the time, f of x is equal to 3x plus 1. Now, notice real quick that its inverse looks like this and looks like this. Why am I bothering saying that? We already know that functions that look like this are continuous. We proved that last week. And that functions that look like this are continuous. Well, we didn't really prove it, but we stated it. This is a, what kind of function is this? It's linear, but it's a
not polynomial.
It's a polynomial. That's a polynomial function, that's a polynomial function. All polynomial functions are continuous, right? And then, those of you in discrete math who did this all the time, it's real easy to prove that this function is also one-to-one and on-two, right? You know what this function looks like? It's just a line. It's going to look something like that. It's one-to-one and on-two. For every x, we only have one y. So one-to-one. And it uses up all of the y-axis on 2. It's one-to-one and on 2. You notice that a lot of this is just about establishing intuition, so we're not really going to prove most of these all the way through. We're just going to make sure that they appeal to your intuition. So, f is one-to-one and on 2, is continuous, and its inverse is continuous, so it's a homeomorphism.
Yeah.
Okay, now let's think about what this function does. What does this function do when you give it some input? So what happens when we pass some interval like AB into this? What does it spit out? 3a plus 1 to 3b plus 1. Right? It takes intervals like this and makes them 3 times bigger than they were before. It stretches them out and then shifts them 1 unit to the right. But it's a homeomorphism. So if I take the real number line, the entire real number line, and I stretch it by a factor of 3 and shift it all over 1, I didn't change its topological structure. the point that we're trying to help appeal to your intuition is that stretching doesn't really change the topological structure of the set, and neither does shifting it. That one make sense? Anything weird there?
Kind of, but it's dealing with infinities, so it makes sense. Like you're stretching it and like.
It's almost like when you say you can
less
zoom up.
in between that interval.
Maybe to help keep your intuition in check, remember this. I think we went over that in this class. Was that not in this class at the very beginning when we were doing set theory stuff?
I don't remember.
If we did, I don't remember.
There's as many the size of the naturals is the same as the size of the integers, is the same as the size of the rationals. No?
These are all infinite.
Huh?
These are all infinite.
Yeah, but they're all the same infinite. For example, this is not the same size as the size of the real numbers. That is a very different infinity than these infinities. These are called countably infinite. No, we did in this class. Countably infinite. We defined what it means to be infinite and finite. Well, we define finite, and then we define infinite, and then we define countably finite, or countably infinite. We did that in this class. But we don't remember these?
I don't see how that helps.
The same notion that just because you increase, if you're kind of increasing by the same factor, because how do you get from the naturals to the integers? You know, one way you can think about it is you're somehow like doubling it, right? And so even when you double it, you didn't really change its size. Oh, I thought that's how you'd think about it. Maybe.
No.
What's the difference between the naturals and the integers? The integers include a negative version of the naturals as well. So for every natural, there's two integers.
I thought we were talking about the rationals and the naturals. Okay. I'm sorry, I don't know how to double. So,
Yeah.
it does make sense if you're doubling it.
And then this one, for every rational, you have z integers, or for every integer, you have z rationals to go with it. That one won't make as much sense if you don't remember how we talked about those, so never mind that one. Okay. Yeah, but another way to say it is that that interval and that interval have the same number of points. The number of points in that interval and the number of points in that interval are the same. It's the same infinite. It's the infinite of real numbers. This infinity and this infinity are the same infinity. The same way that the naturals infinity and the integers infinity are the same infinity. Maybe it's worth reviewing the naturals and the integers at least, because that one's pretty straightforward. How do I show that two sets are the same size? I create a bijection from one set to the other set. So if I can create a bijection from the natural numbers to the integers, then they're the same size, right? Yeah. So let's do that real quick. So I'm going to create f. We'll specify we want it to go. We'll do from the naturals to the integers. By, let's see what we want this thing to do. F of x is going to equal, I think we're going to want, I can't remember what it is. It's going to be something like x plus 1 over 2 if x odd, and then negative x over 2 x even, and I think that does it. So when I plug in 0 here, natural numbers starting at 0, 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. When I plug in 0 into this, then we're going to get 0's even. 0 divided by negative 1/2, or times negative 1/2 is still 0. So it gives me 0. Let's see, when I plug 1 into that, what do I get? 1 plus 1 is 2 divided by 2 is still 1. So then we get 1. When I plug in 3, or sorry, when I plug in 2, what do I get? Negative 1. When I plug in 3, what do I get? 2, then I get negative 2, then I get 3, then I get negative 3, etc. And I'll generate every integer. If I go through every natural, I'll generate every integer. So I could show that for any integer you pick, you can intuitively see it. there's no integer that you can find that's so high that I won't eventually get to it. So every integer comes from a natural number, so it's 1 to 1. Oh, sorry, that's not 1 to 1. So it's on 2. For anything you pick in here, I can find something in here that maps to it. So it's on 2. It uses up all the integers. And then it's 1 to 1 because I only map one thing to that thing. You just have to find the inverse of this to show it's 1 to 1. Does that make intuitive sense?
Yeah.
So there's for that at least. Okay. Anyways. So yeah, taking the number line, stretching it by a factor of 3, shifting it 1 to the right, doesn't change its topological structure. Still pretty much the same. Taking all those infinitely many basis elements and shifting them like this, and they're still basically basis elements. We can write all our basis elements like that just fine. Still the same topology. Right? Okay. So, what are we doing here? Oh, now we're just saying, notice that two things being homeomorphic, the homeomorphic relation is an equivalence relation. So let's make sure we understand that real quick. Now, do we remember what an equivalence relation is? This one we for sure covered at the beginning of this class. And we covered it in discrete math. And we covered it in logic. Comes up 100 times. And we covered it in geometry.
Oh, I see.
It's like our axioms of congruence in geometry is that they are an equivalence relation. That's what those axioms for congruence are. Do the words reflexive, symmetric, and transitive mean anything to you?
Oh, yeah.
Okay. So this relation is reflexive, it's symmetric, and it's transitive. What does that mean to be reflexive? We mean every topological space is homeomorphic to itself. What does it mean to be symmetric? We mean if topological space X is homeomorphic to topological space Y, then topological space Y is homeomorphic to topological space X. And transitive, if X is homeomorphic to Y, Y is homeomorphic to Z, then X is homeomorphic to Z. So let's walk through each of those. We won't do full proofs, but I'll try to give you enough that you feel like you could plug it in and actually do the proofs. So let's really quick do that. It's reflexive. What's the magic function that's going to show that any topological space is reflexive?
So,
The identity function. So we look at the identity function from X to X. It's a homeomorphism, right? Obviously, it maps every point in X to some point in X. Maps every point to itself. And what happens when I pass U into the identity function on X? It spits out U. And what's the pre-image of U? It's U for any open set U. Right? So it's obviously a bijection, right? It maps everything in here to something in here, and everything in here comes from something in here, and everything's only mapped to one thing. And then for any open set U you pick, ID of U is just U, and the pre-image of U is just U. Okay, pretty straightforward?
Yep.
Yeah. Okay, now let's do one that's a little bit more interesting. Symmetric. So we need to show that if X is homeomorphic to Y, then Y is homeomorphic to X. So this time we don't have to find a homeomorphism. We're guaranteed that there is one. So if X is homeomorphic to Y, what does that mean? That means that there exists some function from X to Y where F is a homeomorphism. Right? That's what it means for X to be homeomorphic to Y. It means a function like this exists.
Yeah.
Now notice then that F inverse, yeah, it's so simple, wonderful. Obviously, the inverse of a bijection is still a bijection. And this thing was continuous and its inverse was continuous. So this thing is continuous and its inverse is continuous. And so it's a homeomorphism. And now I'm going to just start using HOM for homeomorphism because my wow, writing the whole alphabet every time you write a word is ridiculous. So Y is homeomorphic to X. Okay, so you feel like you could actually do a rigorous proof of that if you need to, right?
Yeah.
No? You're messing with me? Okay. Because we can do full proofs of any of these that you want. We don't have to just leave that.
prove it with your mouth.
Okay, so now let's look at this one. So we're going to show that if X is homeomorphic to Y and Y is homeomorphic to Z, then X is homeomorphic to Z. And all we're going to use, you might not remember this from last time, but last time we proved that if f is continuous and y is if f is continuous and g is continuous, then g composed with f is continuous.
Yeah.
So we didn't prove it. It was one that I had at the end. I said we could prove if we wanted, but you guys want to leave. So, composition of continuous functions is also continuous. That's all you're going to need to remember here to get this together. And note also that if f is a function from a to b, and g is a function from b to c, then g after f is going to be a function from what? A to C. Okay, good. If you can see that, I think that's the hardest part of getting my explanation here. So now let's read it. So, all right, let's assume that x is homeomorphic to y and y is homeomorphic to z. What does that mean for them to be homeomorphic? That means there exists a homeomorphism for this and a homeomorphism for this. So there exists f from x to y and g from y to z such that they are homeomorphisms, right? Just by definition. So then, g composed with f is a bijection. Okay, that's, I guess we did we prove that? I can't remember clear back to our first chapters if we proved that the composition of two bijections is still a bijection. We for sure did in discrete math, but I don't know if we did that in this class. But that is the case. If this is bijection, this is bijection, then their composition is going to be a bijection. So,
That makes sense.
yeah, it should make sense. Because whatever elements follow through from here to here are still only going to be mapped one way.
Yeah.
Yeah, and when you look at the inverses, same idea. So this is a bijection. Oh, then this is a bijection, and obviously it's still continuous, right? Because composition of continuous functions is continuous.
Right.
And then the inverses of those functions were also continuous, and composition of continuous functions is continuous, so when you compose them together, it's continuous. And notice that this is the inverse function of this, when you take it all together. The inverse of this is that. Does it make sense that the order of these switched? So if we look at up here, let's look at this real quick. Maybe write f inverse here. Should have done that. F inverse now is going to be a function from b to a, assuming that this was a bijection, so we can take its inverse and don't have to worry about anything. And g now is going to be, g inverse is going to be a function from c to b. Does that make sense?
You're going to want to start at C. You go C to B and B to A. Okay?
B to A and C to B. Right, so when we're doing F, when we do G composed with F, remember composition kind of works backwards from what we think. We feed through forward this way. So this is going to take us from A to B, this is going to take us from B to C. So if we want to do the inverse, we've got to start in C. This is the one that takes us from C to B, and then this is the one that takes us from B to A.
Right.
So you got to swap the orders on those. So this took us from A to B, well, sorry, down here it's X, Y, and Z. So this took us from X to Y, this took us from Y to Z, but now this takes us from Z to Y, then this takes us from Y to X.
Yeah.
Okay,
That makes more sense.
so G composed with F is a homeomorphism, and it's a homeomorphism from X to Z. So X is homeomorphic to Z. Anything weird there? Cool. Now let's do some more examples. So here's a cool example. Now we're going to show that the open interval, -1 to 1, with the standard topology, is topologically equivalent to the entire real numbers. And here is our homeomorphism. We're not going to prove it, we're just going to talk about it for a second so you can see it.
And then we thought that plus value was in between absolute value signs.
That's an absolute value right there.
Yes. Right, plus sign. I was like, that doesn't make any sense. Then I realized it was a 1.
Okay, so let's think about what this function does for a second. So first off, when we plug 0 into this function, what do we get?
Just
'Just 0.
Yeah.
Okay. What happens if I plug in a really big number? Let's plug 100 into this function. What do I get?
Close to 100 or close to 1.
Close to 1. I get 100 over 101. right? Really close to 1. So as we plug in bigger and bigger numbers, this thing gets closer and closer to 1. Now let's plug in negative numbers. What if I plug in negative 100?
Also, it's close to
So
negative.
It's getting it closer and closer to negative 1, right? We still have 101 in the denominator, but now we have negative 100 in the numerator. So this function, as we plug in bigger and bigger numbers, it approaches 1 but never quite gets to 1. And as we plug in bigger and bigger negative numbers, it also gets closer and closer to negative 1, right? And now, it might not be obvious to you that that function is continuous, but we could also think about looking at the pre-image of open sets here to see that they're also open. So if I were to take some small interval here, some little interval like that, what's its pre-image? Well, that is going to be from here and to here, so that's pre-image is going to be this open interval, right?
Yeah.
So for any little open interval I pick in the codomain, in the range, then its pre-image is going to be an open interval here. And similarly, every open interval here is going to map to an open interval here.
Right.
So this is going to be, yeah, it's obviously a bijection. We can see that, right? This function is always increasing. It's pretty easy to see. Those ones are all. I don't know if we proved that.
It's not a bijection.
Well, it doesn't
It's
use
not
all of
one, two.
y.
It is onto. Look at the range of this thing.
Oh, okay. Yes.
It's from R to negative 1, 1.
Oh, okay.
So yeah, this isn't from R to R. Good. I should have made that very clear. We're mapping all of R down into just this little interval from negative 1 to 1. And it's still the same size, same cardinality.
Same cardinality of what?
This set and this set have the same cardinality. Furthermore, the topological structure that we get from open intervals here is still the same topological structure that we have here.
Strange.
Take any open set in R, here's one, this open interval, run it through the function, and what you get is still an open set. Furthermore, you get one and only one open set. This goes to one and only one interval, and the pre-image of this is one and only one interval. So you have a bijection not only between the points, but you also have a bijection between the open sets. Make sense?
Yeah.
Okay. Let's just talk about some things in general, and we'll hit to some to try and really make it explicit, but this is all true. So let R have the standard topology, and let A and B be 2 points in R such that A is less than B. We're just going to be talking about intervals. So that's why we're specifying A and B where A is less than B. Consider the following collections. First, all these collections. We're going to look at the collection of all open intervals, so everything of the form AB, negative infinity to B, and A to infinity. And then obviously R. I don't know why I didn't put R in there. All of these are topologically equivalent. They're homeomorphic. The standard topology on this, standard topology on this, standard topology on this, standard topology on this, they're homeomorphic. What does that mean? That means that there's a bijection between the points, all the points in this set and all the points in this set, there exists a bijection between them, same cardinality in the points, and every open set here maps one and only one open set here, and vice versa, obviously. Now notice what we just showed. We just showed that the real numbers are homeomorphic to negative 1, 1. So it should already appeal to your intuition how the real numbers are homeomorphic to any interval like this. But now what might be a little bit trickier for your intuition is, how is something like this homeomorphic to something like this? Or to something like this?
Yeah.
So that's the example that we're going to do. So stopping at 1, don't bother with these for a second. Come down, keep following 1. Here's the bijection that we're going to use. So I'm going to show that R is homeomorphic to this. And we already know that AB is homeomorphic to R. So then, because it's an equivalence relation, this is going to be homeomorphic to AB. So when you're showing homeomorphisms, pick your easiest set because you know it's an equivalence relation. So it might have been a pain to go from this to this. But going from this to this, not so bad. And going from this to this, not so bad. Okay, so let's actually look at it. So we're going to go from R, we're going to map everything in here to one and only one thing in here by this function, e to the x plus a. Now, some of you might not be comfortable with e to the x. It doesn't matter that we use an e here. Could have used a pi, could have used a 2, could have used any positive number here we want. That's greater than 1. We just chose e because it's a common one. And you know what e is? It's just a number, like pi. Pi is 3.14, e is 2.7, or is it 2.7? Yeah, something. So it's just a some number, positive number. We could just as easily replace e with 2. This equation still works the exact same. What's the nice thing about exponentials? They're never negative. They're always positive. Right? When I plug in 0, is the e throwing some of you off? Would we be better off using a 2 here?
That's what I was saying.
2 to the x? Let's look at 2 to the x for a second. Just look at this one. And then the exact same logic holds with e. Looking at 2 to the x. What is this function when we plug in 0? 1. So when we plug in 0, we got 1. Oops, I don't know why I'm doing that. Here we'll put x, here we'll put 2 to the x to try and get a feel for the scene. When I plug in 0, we get 1. What happens when I plug in 10?
2,480.
Now,
4,800.
are none of you working with computers? 1,024. 2 to the 10, 1,024. Okay, now let's plug in negative 10. What do we get when we plug negative 10 in here? 1 over 1,024.
Stays positive.
Right?
Yeah.
2 to the negative 10 is the same thing as 1 over 2 to the 10.
Yeah.
So
Or,
this-
for Peter, this is the multiplicative inverse of this. Right?
Yep.
Okay. So notice that as we plug in larger and larger negative numbers, we get closer and closer to 0. And as we plug in larger and larger positive numbers, we get closer and closer to infinity.
So x can be negative though.
X can be negative, but 2 to the x, 2 to the x is always a positive number. It's going to give us all the positive numbers. There's the right way to say it. It's going to give us all the positive numbers. We can never get 0 out of it, but we can get any positive number out of that thing. I can get as small as you want to get the smallest positive number you can think of, and I can get as big as you want to get the biggest positive number you can think of. And it's a continuous function. All exponential functions like this are continuous. So there's no holes, so we can get all the numbers in between. Make sense?
How can you get closer to infinity?
Pick any positive number you want.
No, you said you get closer and closer to infinity.
This, as we plug in bigger numbers, approaches infinity. The function approaches infinity as we plug in bigger and bigger numbers.
There it is. It's just that like it's not real numbers.
No, it's an extended real number. The extended reals are the real numbers with negative infinity and infinity as members. But approaches infinity is standard terminology for it's unbounded. It gets bigger and bigger without any bound. Or it gets arbitrarily large is another thing that is another way we can say the same idea. Anyways, okay, we were over here. So this e to the x, all you need to know about it is it spits out any possible positive number. Right? I can get any positive number out of this, but I can't get 0. But I can get slightly more than 0, whatever that means. And then plus a. So now when we graph this thing, a is going to be a horizontal asymptote. So the whole function gets shifted up by a. So it has to be at least a. And then this is always positive. So I can't ever get a. I can only get slightly above a. So you see how the image of this thing is that interval? We can't quite get a, but we can get every positive number above a. This gives us every positive number. This gives us a. Put them together, we get every positive number above a. And so it looks something like this. Good?
Yeah, we can get negative. You can't get negative.
I cannot get any negative numbers out of this. Well, depending on what A is. If A is a positive number, like I did it in my picture, but A could have been down here and then it would have been a function like that, right? So, but this can't ever give out a negative number. Okay, so that was showing open intervals are the same. So we showed that this is the same as this. We kind of showed, we didn't really, but we kind of showed that this is the same as this. We did it for a particular AB, we just did it for this one. But it wouldn't be hard to show that this is the same as all ABs, and so we'll do a similar thing except for with closed intervals, and then you can use the same logic here. It's the same function. Anyways, so we finished number 1, we're going to move on to number 2 unless you have any questions about number 1. Does it appeal to your intuition that all these open intervals are going to be homeomorphic with the standard topology? Yeah. Alright, so let's move on. Closed bounded intervals. Now, why on earth did we put that bounded word on there? Why aren't we just showing closed intervals? Because R is open and closed. And we very much expect this to have a different topology from this. And they do have different topologies. So, we're just showing that closed bounded intervals are all homeomorphic. This does not include R. Make sense?
Wait, what does bounded mean again?
It doesn't have any infinities. This is unbounded, this is bounded.
Okay.
This is bounded, this is unbounded, this is unbounded. So this is a closed interval. This is a closed set in the standard topology. This is a closed set in the standard topology. But we're only saying that all these are the same. Make sense? So now let's do that. That's number 2. So number 2 is right here. Here's how we're going to do it. I'm going to show that 0, 1 is homeomorphic to any AB you choose. So 0, 1 is homeomorphic to any closed interval like this. And so now if I'm wondering, well, is the closed interval 2 to 7 homeomorphic to the closed interval -3 to 13? Once I prove this, the answer is yes, because this is the same as this is the same as this. And so they're the same. This is a very good syntax because I didn't include the topology there, right? I just did the sets. And these also have the standard topology that they inherit from R. So don't read too much into that. Anyways, understand what we're trying to prove?
Yep.
And understand how showing this shows us that all closed bounded intervals are going to be homeomorphic to each other. Because they're all homeomorphic to this, using transitivity, they're all homeomorphic to each other. Okay, so let's look at our function. Function, really simple function. This is a great function that comes up in math all the time. Very useful. G of x is equal to b minus a times x plus a. Now notice, first of all, that this function is increasing. As you plug in bigger values of x, you get a bigger value out. A and b are just constants, so x is increasing. So this is a function. Here's the slope. I guess also remember b is bigger than a, so b minus a is a positive number. So it's just going to be a line with some positive slope, with some y-intercept. So here's what it looks like. But notice it's only defined on a closed interval 0 to 1. So it's a line with some positive slope, only defined from 0 to 1. Looks something like this. And it's increasing. What happens when I plug a into this function? Or sorry, what happens when I plug 0 into this function? The smallest value I can get out of this is when I plug in 0. When I plug in 0, what do I get? A. I just get a. When I plug in 1, what do I get? B, right?
Yeah.
Plug in 1, we get b minus a plus a, just gives us b. So the smallest value I can get out of there is a, the biggest value I can get out of there is b, and then this line is obviously continuous, so I'm going to be able to get every point in between. So the image of it is going to be everything from a to b, including a to b. Does that make sense? Okay, So now we know that all closed bounded intervals are homeomorphic to each other. Now let's show that all half open intervals are homeomorphic to each other. And this one, we can't prove all the combinations, so I guess I'm just showing that this one's homeomorphic to this one. But they're all homeomorphic to each other. So let's do that one. So I'm going to show that things that look like this are homeomorphic to things that look like this. So I'm going to do h is a function from a to infinity that goes to negative infinity to b. And my function is just going to be negative x plus a plus b. Pretty straightforward? Now notice, once again, this is just a line, but now it's a decreasing function. Right? It's a line with slope negative 1, whose y-intercept is a plus b, whatever that is. That's all it is. So it's going to look something like this. I gave it a slope of way more than negative 1, but should have made this line out more like that. But the thing to note here is that what is the biggest number I can plug into h? Or sorry. Since this is a decreasing function, then the smaller the number I plug in, the bigger the value that comes out, right?
Yes.
So the smallest number I can plug into this function is a. Here's my domain. The smallest value of my domain is a. When I plug a into this function, we get b. So b is the biggest thing I can get out of this function. So when I plug a into the function, I get b out of the function. And now for any number bigger than a that I plug in, I'm going to get a number smaller than b that comes out.
Right.
So this function is going to give us b at the most, and then any any number less than b, we can also get out of this function. So it's a function from here to here, and obviously it's a continuous function, its inverse is continuous, it's 1, 1. It's a homeomorphism. So we show that things that look like this are homeomorphic to things that look like this. Good? All right. So there's some intuition about some of the common intervals we work with just in the standard topology on R. Because that's the topology we typically work with. Let's do, well, in my mind, a more interesting example, but that's for you to decide. So now let's look at the interval 0 to 2 pi including 0. This is as a subset of R, so it has a standard topology. And S1. S1 is a circle. Okay? And we're also going to give it the standard topology that it inherits from R2. So this is going to get the standard topology from R1, and this is going to get the standard topology from R2. Remember what the standard topology looks like in R2? Open balls. So here's my circle, first of all. What do open sets in my circle look like? Pick an open set in R2. What does an open set in R2 look like? Something like that, right? So now where does that intersect the circle? It intersects it from here to here. So these open intervals on the circle and unions of those open intervals are what open sets look like on the circle. Good? Similarly, this is just on R. So pick any open interval on R, like that, and however it intersects this thing is going to be an open set here. So from here to here, that's a possible open set. Or just some small internal interval like that, that's an open set. Or if we take the open interval here and intersect it, then that's going to be like that, is an open set. These are subspace topologies. This is as a subspace of R with the standard topology. This is a subspace of R2 with the standard topology. With me?
Yeah.
You know the two topologies we're talking about? Okay. So now, here's what our function does. We'll read it up there, but first let me go to the picture, and then I think you'll make sense of what I'm saying. What do? So this is from 0 to 2 pi. Notice that that's how many radians are in a circle. Right? So what are we doing? We're saying pick the angle here, and we're going to map this point to whatever point is at that angle here. So if you choose, not pi, that's supposed to be theta. If you choose theta, call theta your point in here, then the point on the circle at angle theta is the point it maps to here. You with me?
Yes, sir.
So pi maps to pi. And really close to 2 pi maps to really close to 2 pi. And then we get back to 0. What? Is the 2 pi what's throwing you off? Let's try this a different way.
No, I understand.
Let's go to 360. Doesn't change anything. We'll call that theta. And then we'll call this a point at that angle.
What do you mean the point at that angle?
Yeah.
That's why I'm getting lost.
Pick some number between 0 and 360.
180.
180, right? So now go to 180 degrees on the circle. That is right here. We're talking about that point. 180 maps to this point.
Okay, but how can you talk about stuff like that when you haven't even like talked about it?
It's a graph.
When we have a what?
What
I'm
trig-
still lost. How can you like what?
How can you like what?
I don't get what you mean by that angle. How can you create?
Okay,
You haven't even done angles yet.
Ooh, we can't go over that. I just realized all that's not in the video. You guys can't really go past that squiggly line. Angle measures, we always start from the x-axis like this.
Yeah.
So 180 degrees is this. 180 degrees.
Okay, I know that, but we haven't talked about that at all in this class.
Yeah, this
These
is an
are
example.
just examples. Remember that we're going to, so as we're going through this course, we keep doing two things. We rigorously develop the topology, and then we jump into areas that we haven't rigorously developed, that you are supposedly already familiar with, to see examples of topology.
Okay, so this is just telling you you're supposed to make this a measurement of an angle. That's what that circle does.
We're just creating a function that maps this point right here to this point. It maps this point to somewhere down here. It maps this point to this point. It maps every point from 0 to 360 to a point on the circle.
Okay.
And what point does it map it to? Measure that angle out on the circle, and whatever point is at that angle, that's the point we map it to.
Okay.
We're just trying to come up with a simple bijection, so that for sure we map everything here to one and only one point here. We're just trying to use examples that are very intuitive to you, so I don't need to prove that this is actually a bijection. You know that for any angle you pick between 0 and 360 degrees, there's a point on the circle corresponding to that angle. That's all we're saying here, or 2 pi. Same thing, right?
Yeah.
Everyone okay with the 2 pi there, or should we go back to 360? It makes no difference. Good with the 2 pi? Okay. So, that's what the function does. Okay, so 0 to 2 pi and S1 have the standard topology as subspaces of R and R2. And now we have F is a function from 0 to pi, so this is its domain, and its output is S1 by F of theta equals a point at the angle theta. Good?
Yeah.
Okay. So now, we could have just as easily said, if you don't mind polar coordinates, we could have said 1 comma theta and made it a circle of radius 1, if you prefer it that way. I don't know, more confusing, less confusing? Keep it how it was?
Either or.
All right. Okay, so let's look at this function. Is this function a bijection? Is it a continuous function?
Yeah.
Yeah.
It's not.
I think so.
Oh.
So this is a homeomorphism, right?
Yeah.
And so this topology and this topology are the same. No.
Fine.
And hopefully it appeals to your intuition that this topology and this topology are drastically different things.
Because they don't connect.
Look at this. Is this point anywhere near a point over here? No. Are they in this picture? Yes. Proximity is not preserved. If I map from here to here, we change proximity. We made points close that were not close before. Or if you want to think about going that way, here we had points that were close, and now they are nothing like close. These are not the same topologies, and it should be screaming at you, no, these are not the same. Another way to think about it, rubber sheet geometry. I give you a circle, and I say, now make this. No breaking the rubber band though. No making points close together that weren't close together before. You can't do it. The only way to do that is to break the rubber band, right?
Yeah.
So it should be screaming at you, no, these two are not the same topologies, not by a mile. That should be as obvious to you as me writing something like this. Now, drastically different, right?
You could make a rubber band into a triangle.
Oh, sorry, I meant congruence in geometry.
Oh.
Sorry. I forgot that we use that same symbol. In geometry, if I told you that a triangle is congruent to a square, you know, no, you're talking nonsense, and if you think you have a proof that shows it, you don't, and there's a mistake in the proof.
So,
So
what was wrong?
here we've got this continuous function, and it's a bijection. What is wrong with this function?
It's not.
The inverse is
The inverse is
a continuous.
not continuous. F inverse is not a continuous function. In other words, so if you look at an open set here and look at its preimage, it's going to be an open set. So let's make sure that that makes sense. Pick any open set here that you want. Well, if you pick one like this, what's the preimage of that going to be? It's just going to be some open interval in here. That wasn't very interesting. That was easy. The tricky one to pick is let's look at the preimage of when we pick something that includes the point 0, right? What does the preimage of this look like? Well, this part of the preimage maps to right here. That's an open interval. Oh, sorry, that's this part. This part of the preimage maps to right there. That's an open interval. This part of the preimage maps to right here. That is still an open interval. Or still an open set in this topology. It's the intersection of this open interval with the set. Remember, we're talking about subspace topology. So this is open, this is open, this union, this is open. So the preimage of every open set here is open here. Now let's go the other way. Let's look at the image of just this. What does the image of just that look like? It looks like this, starting there, going to there. That is not an open set in this topology.
Okay.
So the function does not map open set to open set.
It's not
Here's an open
over
set.
there. It's not open right there. It's closed right there.
This is open. It's also closed, but it's open.
That's closed, but it's open too.
Oh wait, no, this one isn't closed, sorry. But it is open. So this is open, but this is not open. I cannot create an open ball and intersect it with this circle and get that. I can create an open interval, intersect it with this number line and get that. This is an intersection of an open interval with this whole set. This is not an intersection of an open ball with this whole set. We're open over here, our image isn't open. So F inverse is not continuous. So it was a bijection that was continuous, but the inverse function was not continuous. So the bijection has to be continuous, and the inverse has to be continuous. And just having two of those properties does not give you the other one for free. Good?
Yeah.
More interesting example. And it better scream at you that those are not the same topologies. Those are drastically different things. Very, very different. If it didn't, you need to go back to your intuitions of topology and rethink about it. There's two intuitions that we've given you so far for what topology is. Rubber sheet geometry, if I give you one shape, only by stretching and pulling whatever you want, reshaping it, essentially, can we get it from this to this? No. The really good way to keep a topology straight in your head, the great intuition, is it preserves proximity. Can I take this and make it look like this and preserve proximity? Keep every point close. Every point that was close here is still close over here. And no points that weren't close here are close here. So all the points that were close have to stay close, and all the points that weren't close have to stay not close. It preserves proximity. That's ultimately what topology gives us, a way of talking about proximity. So this has points that are close that are not close over here using this mapping, right? Namely, this point and the point right after it. There isn't a point right after it, but I think you understand what I mean. right? Okay. So we're good with that picture, and I'm ready to move the camera.
Yeah.
Now you guys are going to kick yourself when you go back and watch the lecture. You can't see what I was writing there. That is just exponential function stuff. That's not your let's erase it without erasing the important stuff. Get rid of that, and that. All right. Now we're going to be talking more picture stuff, less actual equations. And so hopefully my pictures are good enough. We'll see.
They actually look pretty good this week.
This week. All right. Sounds like we did good this week. Okay. So here's what we're going to prove, and what I'm trying to show here. That the entire real number line, or the entire real plane, R2, is homeomorphic to the half plane, is homeomorphic to the open disk. That's what those three pictures are meant to represent. You with me on that?
Okay.
Okay. So first I'm going to show that R2 is homeomorphic to the half plane. I just called it H. And the half plane starts at some number A. Here's a function to do that. Remember, okay, make something clear here, because you probably aren't comfortable with these. F now is a function that takes two inputs and spits out two outputs. It's going to take a point in R2 and spit out a point in R2. F is a function from R2 to H, which is a subset of R2. So it's taking in ordered pairs and it's spitting out ordered pairs. Okay?
Okay.
So it might look weird that I'm doing something here, comma, and then I could have had some other math over here. Okay, so let's look at what this function is doing. So we're mapping all of R2 into just a half plane. How are we doing that? Well, first off, we're mapping the y-coordinate just to the y-coordinate. So this point right here, when I map it over here, it's going to have the same y-coordinate, and only its x-coordinate is going to change. That's what this is saying. Y still just goes to y, but x goes to this now. So this is not plotting x versus y. Here's our x, now here's our y. Usually when we draw a picture like this, and we say a line, we said, here's our x, here's our y. It's mapping things here to things here, like this. This is showing the relationship between them. That is not what we're showing here. This is now our domain. This is now our range.
Okay.
Okay. All right. So now, here's what our function is going to do. We're going to match y, but now here's how it's going to map x. It's going to map x to e to the x plus a. Now all you need to remember is that e to the x can give us every possible positive number. And then we did plus a. So now this is going to give us every positive number. Well, it's going to give us a plus any positive number as an output, right? So we're never going to quite get a, but we'll always get things slightly bigger than a and as much bigger than a as we want. So when we take a point like this and we plug it in there, then that's going to come out, oh, I don't know, somewhere like, I don't know, that's a negative number, so somewhere like right there. Who knows? But the point is, if I were to pick a point way over here close to negative infinity, that gets really, really close to a here. And points that I pick clear out here are going to be clear out here still. So I feel like you got good intuition for what this function does. And you see how it maps all of this to this. And then it's a continuous function. How do you show functions like this are continuous? You show out their individual parts are continuous. So this to this is continuous and this to this is continuous. So the whole thing's continuous. Or, using our topological notion, you just need to look at the pre-image of open sets here, to see if they're open there, and they are. And then look at the image of open sets here, see if they're open sets here, and they are. Okay, so that's what F does. So we just barely showed F takes this, maps it to here, here's the way that does it. Okay, now we need to show that these are, because now we know these are homeomorphic to each other, we need to show they're also homeomorphic to the open disk. Okay? Easiest way to do this one is with polar coordinates. Has anyone in here not come across polar coordinates before? Yeah. Okay, then let's go over it.
An angle.
So when I tell you, when we're looking at coordinates, and I tell you we're going to the point 4, 1, what does that mean? It means we're going to go 4 units in the x direction, and then 1 unit in the y direction, and it gives me this point. 4, 1, right? Notice it's like giving me directions on how to get from the origin to this point. So if you're trying to tell me how to get to that point, you can tell me, Donnie, you need to go this far in the x direction and this far in the y direction, and you can tell me how to get to any point. Now there's another way that you can tell me how to get from this point to here. You can tell me, Donnie, you need to aim at this angle theta, and then you need to walk this distance r. So instead of telling me to go 4 units this way and 1 unit that way, you tell me turn however many degrees it is, and then just walk however far the distance is. And then I can get to that point. That's polar coordinates. So polar coordinates is just r comma theta instead of x comma y, where r is how far you walk and theta is the direction you walk. So this tells you go this far in the x direction, this far in the y direction. This tells you, no, you're just going to go this far and just do it in this direction. Make sense? So that's polar coordinates. And polar coordinates, we can map out the entire real number plane with polar coordinates. So a point right here, this might be the point, I don't know, let's say that this was a distance 7 away, and the angle there looks like it's roughly pi fourths or 45 degrees. Usually we do radians 7 degrees because they're far superior. And so I can map out all the points in R2 with polar coordinates, right? So now our function, we're not going to show that this is homeomorphic to this. We're going to show that this is homeomorphic to this. But since this is homeomorphic to this, then you get it all for free. Well, so we're doing this to this. That's what G is going to do. G's right here. So G is going to map all of R2 to the open disk. How's he going to do it? You give it a radius and a theta. It's going to map to the same theta. But now it's going to take R, and it's going to map to R over R plus 1. And we've already seen a function that's almost exactly like that. That was over here. R is always a positive number. Well, it doesn't have to be, but you could always reword the coordinates so that R is positive. So we can think about those as always being positive numbers. So you get a number over a number slightly bigger. So this, as R gets bigger and bigger and bigger, as we use points further and further away, over here we get closer and closer and closer to 1. This circle has a radius of 1. Things aren't to scale. Does that make sense? So this point here still gets mapped to this point here. This point here might get squished a little bit. This point here is going to get squished like that. And once we get out there, it's going to get squished like that. And as we get way out there, it's going to get squished more and more and more, getting closer and closer to that edge. Make sense?
Yeah.
Okay. So that's this function. All right, so there we go. We saw those three things are homeomorphic to each other. They're all topologically equivalent when you give them the standard topology that they inherit from R2. Good? All right, let's do another example. I couldn't do this. I have no clue how to draw a picture of this. So first we'll do it in this case, and then we'll go up to it. I was supposed to show that the surface of a cube, C, is homeomorphic to a sphere. The surface of a sphere. Sphere is just a surface, right? So here is the way that you can think about it. So I'm going to talk about the circle being homeomorphic to the square. And you don't need to think about the square doesn't have to be the exact same size as the circle, but maybe it helps you see it. All we're going to do is we're going to radially map out the points just like that. Radially map it out. So that point gets mapped to there. This point gets mapped to here. This point gets mapped to here. This point to here, 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 here. This point gets mapped to here. This point gets mapped to here. That's how we would do it. And if you imagine an open interval here, when we map it out, it's going to still be some sort of weird open interval thing like that, right? And that is still going to be the intersection of some open circle with that box. You with me? Now notice that that would be the exact same case. We didn't need to have a circle this big. I could have had the circle teeny like that, still done the exact same mapping, would have worked out the exact same way. Does that make sense? So now a sphere inside of a cube, this room's almost a cube, it's kind of close. So if you think about this globe, yes, that works. The globe, and you take each point on the globe and just map it out from its center. Or maybe think about if the globe were some sort of light source, and it was just shining. And you thought about all the individual photons and where they land. If this room were a perfect cube, every photon would land to one and only one point, right?
Yeah, like a disco in a room.
And it would still light up the entire room. So every point would get hit by a photon, and each photon, imagine that got perfectly absorbed, so we had a perfectly black room, would hit that one and only one point, right?
Disco.
Disco. That helps you think about it all right. So, nobody will be able to draw that, but I think if you understand the square, then going to the sphere is pretty easy.
And it doesn't have to be a square either, does it? Can it be rectangle?
It could have been a rectangle, and you could have stuck it in some sort of rectangular prism, and it would still work. The intuition is, if it were a light source and I stuck it inside of there, would it still shine points everywhere? Make sure that you don't end up with a shape that couldn't shine points everywhere, otherwise you're going to eliminate it being a bijection.
What about a triangle?
Yep, triangle still works. Could put the circle inside the triangle, still works. Is that one not obvious?
No, it is. I was thinking of like 3D triangle. Like if there's a triangle prism and then there's like a pyramid.
Works with both. Okay. So, that's that one. Now here's the one I was really worried about. So first, let me just try to give you intuition for it without looking at the picture, and then we'll go back to the picture. So imagine I had a sphere, but now we poke a hole in the sphere. And think about it in terms of rubber sheet geometry. So I've got a sphere with one little hole poked in it. I can take that hole and I can stretch that hole out, right, and flatten that sphere into a disk.
Yeah.
Yeah? And now I can take that disk and stretch it into all of R if I wanted.
Yeah.
Right? So that's thinking about it in terms of intuition that we might already have for what you can and can't do with topologies. So I can't take a sphere by itself and squish it. Right? There's no way for me to do that. I'd make points that weren't close suddenly close again. But if it has a hole in it, I can now stretch out that hole and not put any points close that weren't already close. I can stretch it out as much as I want. Does that make sense? Okay. So here's how we're going to show what the actual homeomorphism is that you would use.
The surface of it?
Yeah, just the surface of a sphere.
You poke one hole.
Just the surface.
Like
And we
one
poke one little hole in that surface. So it's a balloon. We got a balloon.
Okay, now I got
And
it.
we poke a hole. And now it's a balloon that, you know, it's never going to rip. And we can stretch it as much as we want and it still won't rip. That kind of balloon.
Wow.
So once you poke a hole, I can stretch that hole as much as you want without ripping the balloon, right? I'm just stretching the rubber more and more and more. It's got infinite stretchability. And we can stretch that out as big as we want now. So you take a balloon, you pop one hole in it, I can flatten that thing out to a nice disk if it's got infinite stretchability, right? And a nice disk can become R. That's no problem.
Wouldn't there be like a hole in R then?
No. The hole is what ends up being your boundary.
Yeah.
The hole, you stretch to infinity.
Yeah, you make your triangle
in every direction.
interesting on.
So you
That's
start out,
so messed up to think about.
there's our sphere, and we've got one little hole that we poke in it. We grab that hole, and now we can stretch it, and stretch it, and stretch it, and stretch it.
Okay.
And my sphere is going to level out, right, and get more flat. And as I keep stretching, I can stretch that thing to infinity. So I stretch it out, get a nice disk, and I can stretch that disk out to infinity, still the same topological space. Yeah, the geometry is all sorts of screwed up, but the topology is preserved. Same topology. Okay, so that's how I try to give you intuition that, okay, yeah, I can see that punctured sphere could be the same as all of R2. Now I'm going to try and give you intuition for how that homeomorphism goes. This is going to be kind of hard to do. Let me use the globe. Glad we have this. All right, here's what we're going to do. So S2 is a sphere, and we're going to assume that our sphere here just has radius 1 and is centered at the origin. So the top point is going to be 0, 0, 1. 0 in the x direction, 0 in the y direction, 1 in the z direction. Z is going to be up, and we're on the xy plane. And I'm going to map this thing to the xy plane. That's what I'm going to do here. You with me so far? So how am I going to do that? So I got the sphere, I'm going to poke a hole in it. Now, the xy plane is going to come through the equator. That's nice that we have that. So imagine the xy plane at the equator to infinity. Now, pick any point on the xy plane that you want. So pick a point like where this water bottle is. That's roughly the same height, right? So pick a point right here at the center of this water bottle's lid. Make the line that goes from where my punctured hole is to the center of this lid. That is going to intersect the sphere at one and only one point. So my line's going to be inside the sphere because we're punctured here, and then it's going to come out of the sphere at one and only one point to hit the middle of that lid. That's how I'm going to map that point to the ground. And this whole patch would be mapped to a patch right here. So some open patch here would be mapped to an open patch here. That's the way that the projection works. We're projecting the sphere onto the plane. So that's projecting outwards. So to get to this point here, so I draw a line from N, it's going to come out, hit the sphere at some point P, and then where it hits the XY plane, we're going to call F of P. It's going to map that point P to F of P there. Does the picture make sense?
Yeah.
Okay, so that's for all the points outside the sphere. Now, we have to picture the XY plane also goes inside the sphere, right?
Yeah.
So now, when I point my line like straight down, it's going to come out the bottom, right? So I'm mapping the bottom now point to wherever it intersected the XY plane, which is right at the center of the sphere. And so I'm mapping this point. If you take the point right here on the globe, think about the line between this point and up here. Where does that intersect the XY plane inside of there? That's the point we map it to. So all the points at the bottom of the sphere get mapped to points inside the sphere on the XY plane. And then all the points, obviously, on the sphere just come from themselves. And then all the points outside the sphere come from points up here. So the top half of the sphere gets mapped to everything outside of it. This circle that is the equator of the sphere, if you want to think about it that way, just gets mapped to itself. And then everything under the sphere gets mapped to the XY plane that's inside that sphere. Does that make sense?
And they'll all only hit one point on the sphere.
They'll all hit one and only one point. The inside part, once you see that, I think that's the easier part. It's the outside part. The crazy thing is that, yeah, the inside part, we just like, it's almost like just looking at a shadow almost. Not quite, but pretty close to just looking at a shadow right there on the XY. The crazy part is this half of the circle, without one point, gets mapped to the entire plane, except for that inside disk. Good? That is called the punctured sphere. Okay. Let's do some more. Next we're going to look at, this is an annulus, but we're going to view it as a cylinder, because we're going to view it in R3 rather than R2. So we're going to look at the circle crossed with the closed interval -1 to 1, and it's going to give us something like this. Does that cross section make sense? Okay. -1 to 1, we'll graph it in the y direction. Here's -1, here's 1. And now we're going to cross it with the circle, which means to every point here, we're going to assign a whole circle to it.
Yeah.
So to this point, we assign a circle. To this point, we assign a circle. To this point, we assign a circle. And we keep doing that for every point here, we assign a circle to it. And you're going to end up with a cylinder. This is hollowed out. Sorry. We're talking about same thing as if you like rolled up a paper. Same thing is something like this. This is -1 to 1. We assign a circle to each point on it.
Okay.
So that closed interval, any closed interval, we just pick -1 to 1, why not? But any closed interval crossed with the circle looks like a cylinder when you're talking about an R3. If we're talking about an R2, it's just an annulus. Notice I can take this thing and flatten it out and get just like a washer looking shape. Okay. So that's a three-dimensional figure. Now we're going to make a quotient topology on this thing. What's our quotient topology going to be? All we're going to do is assign, maybe keep this. This is easier than talk about a picture. So we're going to assign every point at the top circle, every point at the top of this to the same point. We're going to identify them together. You remember identifying a set of points as the same point?
Yeah.
So we're going to make all the points at the top the same point. We're going to make all the points at the bottom the same point, and every other point we're just going to let it be its own point still. You with me on that? Or do you not remember identifying points together? Let's look at a simple example of identifying points together to remind us of the intuition. So imagine I had just interval from A to B. You with me?
Yeah.
Just close the interval A to B. Now I'm going to identify this point with this point. I'm going to make them the same point. That's going to give me a circle.
Yeah.
Okay.
This point is still its own point, this point is still its own point. Every other point is still their own point. It's just I made this point and this point the exact same point, which gave me this. You might have remembered doing one like this. So we've got some square like that. And I decided I'm going to identify all the points here with the points here. Every other point gets identified with itself. I identify all these points with all these points. And that gave us a strip. So I had something like this. If I take all the points here and identify them with all the points here, we have this. And we said, well, what if we reverse the direction? So I identify all the points here with all the points here, but I identify this point with this point with this point, and now a point right here would be identified with like a point right there. So that is when we get how we get the Mobius band. So instead of identifying it like that, I flip it as I identify it, and we got the Mobius strip.
Yeah.
Okay, same concept that we were doing when you saw these arrows gluing points together is some of the terminology that's sometimes used. We glued these points with these points.
What does that just mean? A sphere.
Perfect. That's exactly what the question was. It's going to be homeomorphic with S2. So if I took this thing and did exactly that, I identify all the points on the top together and all the points on the bottom together, I'm going to have some closed shape on the top and bottom, and it's homeomorphic to the sphere. In other words, imagine I put a little spherical light source in there and I glued all those points and all those points together. That light source would shine every photon to one and only one point on there, if that's a helpful way to think about it.
It would be a sphere.
A sphere. It would be homeomorphic to a sphere.
Oh.
It'd also be homeomorphic to a cube.
Yeah.
The surface of a cube. I think a cube includes a poly, but the surface of a cube. So, yeah. S2 is what the book actually says, but yeah, you could have also said, and the surface of a cube. Same thing. Because we we talked about over here that the surface of a cube is homeomorphic to S2. So if this is homeomorphic to S2, then it's homeomorphic to the surface of a cube. Homeomorphisms are symmetric, transitive, reflexive. Okay. Now, question on these ones. Tried drawing that, knew that was a mess, and that's why I created this strip. Here's what we're doing. So we started out like this, that's what we have over here. And now I'm not twisting it once, that's Mobius band, but I'm twisting it twice. So we still have two sides. The purple side is still the purple side, and you can't get from the purple side to the white side without going over the side here.
Right.
So remember that the Mobius band only had one surface, right? The Mobius band was like this. It's possible for me to get to the white side and then to the purple side and then back to the white side
Yeah.
just by moving on. This is not the Mobius strip. It's flipping twice. Okay? So you feel like you understand the shape we have here?
Yeah.
Okay. Yeah, now you know why.
I mean, your picture looked a lot better.
Oh, really?
No.
No.
Okay. Anyways, so we're flipping it twice. The question now is this thing homeomorphic to this thing?
Yeah.
Can I deform this thing without, in terms of rubber sheet geometry, can I deform this thing and make it look like this thing? Deform this thing and make it look like this thing? Or is it possible for me to start out, should be able to go both ways, is it possible for me to start out with this thing and go to this thing in rubber sheet geometry? I can pull, stretch,
Oh, is it Mobius band?
I can twist it, nope, not the Mobius band, but if I twist it, what does that do? That's not the same thing.
Put it inside of itself.
The only way for me to go from this shape to this shape is to have it cut and then put it back together.
Really?
Really?
That's the only way to do it.
Are you sure?
Yeah.
If I take this together like this, you will not be able to get it into this shape. I am sure of that.
Okay.
Yes. Because any rotation, it would force a rotation on the whole thing. I mean, that isn't really twisted in terms of topology. It's the same as this. But this is fundamentally something different. I can't untwist that without breaking this. There's no way for me to untwist.
Oh,
Twist up there.
because both your twists are going in the same direction.
Okay, that makes sense.
Right? I can't, there's no way for me to untwist that without letting go of how I'm holding the pieces together. The twist is always there.
Right.
Every time I add a twist, well, that's not good to say about. So the question, are these topologically the same? Are they topologically equivalent? What do we think?
I would say no, yeah.
I'd say no, yeah. Well, I'd say yeah, no.
I don't know.
I know you don't know, but what appeals to your intuition? Yes.
That strip
We're all
right there, so
representing
if they're not.
When
Yeah,
I look at it, it appears like no, because
because you'd have to break it.
You would have to break it. There's no way around it. You'd have to cut it and then glue it back together. Okay, here's the important thing to know with how I had it before. So see how it is. See which points are close to which points. When I cut it and glue it back together, are those same points still close to each other?
Yeah.
Yes, they are. Every point that was close to each other, imagine I could somehow like fuse that back together. All the points that were close to each other are still close to each other. So this is the one place where the notion of rubber sheet geometry
Just not.
kind of misleads us. And so we don't make very clear what exactly we mean by rubber sheet geometry until chapter 12, which we might not even cover in this class. But, so rubber sheet geometry can be somewhat misleading. The intuition that will never lead you wrong was proximity preserved. All the points that were close to each other when I hold it this way are still close to each other when I hold it this way. Does that make sense?
Yeah.
Proximity is preserved. All the points that were close to each other are close to each other, and no points that weren't close to each other are now magically close to each other. So we didn't add any proximity, we didn't remove any proximity. Draw any open set you want on this thing when it's like this. When I undo it and put it back together this way, that set is still open, and vice versa. That's another way that might help you. I don't know. So a bit of a gotcha if you just think about in terms of rubber sheet geometry, you might not think that those are the same. But if you think about it as preserving proximity, or if you thought about let's draw any open set on that thing we want before we cut it, put it back together, that open set is still going to be the exact same thing. Maybe one more way that might help your intuition out now. If you were some two-dimensional being that lived on this thing, if I had it like this or I had it like this, you wouldn't be able to tell the difference. But if I had it in a Mobius band, that's a very big difference. Right? Because now there's only one surface as opposed to two.
So when is topology even like useful if it's only with proximity? Like that's hardly any.
With just proximity, we are already able to talk about continuous functions.
Yeah.
We could already define a derivative in calculus. We could define a derivative on the real numbers in standard topology, and we don't even have a metric yet. We don't have a metric space yet. Metric's what you want, by the way. Metric is what gives you distances. Once you have metrics, you have distances, and then you're all happy again. Because now your distances have to be the same. Not only do points that were close have to be close, but now distances also have to be the same. So that's going to get us closer to actual geometry. Okay, we all good with that example?
Yeah.
All right. I'll say that at the end of class. That's not relevant for this. Next, down here, an embedding of a topological space. Okay, so we have x and y are topological spaces, and we have f is a function from x to y. Notice we did not say this is a homeomorphic function. We did not say this is a bijection. It's just a function from x to y, but it maps f, but that maps, that's an X. That maps X homeomorphically to a subspace f of X in Y. So the function f maps X homeomorphically to f of X, which is a subspace of Y. So it's not onto, it doesn't map anything to that point right there. It maps all of X to this weird looking subspace in Y, but it does it homeomorphically. In other words, you look at an open set here, it's open in the subspace topology that this thing inherits from Y. You look at an open set here, it's open when we come back and look at the preimage here. And it maps everything in X to one and only one thing in f of X. So in other words, if we were to restrict the image to f of X, then this thing is a regular homeomorphism again. So it maps X homeomorphically to a subspace f of X and Y. Does that make sense?
Yeah.
So now, two very important definitions for, at least for physics. If f is a function from some closed interval, -1 to 1, but it doesn't really matter what the closed interval is. If f from -1 to 1 to x is an embedding, then the image of f is called an arc in X. So, here might be our X over here, and the image of f might be this line right here. This line over here in X we're calling an arc. The other common terminology used for it is a curve. This is a curve in X, or an arc in X. And then if f from S1 to X is an embedding, then the image of f is called a simple curve in X. That's one that's very useful in complex analysis. That's calculus with complex numbers. Use simple curves a lot.
How's that curve useful in physics?
This, when you talk about the path of a particle, it's going to be like this. Because in physics, not basic physics, when you're talking about like general relativity and the path of some object in general relativity, then it's going to be like this. Once we get to at least a manifold, if we get there, then this will be how we talk about like a path on a manifold. Okay. Any questions with those two? Okay. So one little theorem to go through, one little conversation to have, and then we're done. So I'll move this over. And there are no more markers in here, so I hope that that is readable. Okay. So, back to what we said at the very beginning. We said homeomorphisms tell us that topologies are somehow equivalent. And if I want to show that two topologies are equivalent, how do I do that? I need to show that if you give me two topological spaces, I can find some homeomorphism between them. That's how we show that they're homeomorphic. What about if they're not homeomorphic? And I spent my whole life trying to find some homeomorphism to go from one to the other. How do we prove that they're not homeomorphic? We can't check every function from x to y. Well, in some cases we can for really, really simple ones like what we started with. But as a general rule, we can't check every function from x to y to rule out, oh, these two things are not homeomorphic. Now, what we're going to prove as topological properties come up, like Hausdorff is a topological property, as these topological properties come up, what we mean by a topological property is that homeomorphisms maintain these structures. So if x is Hausdorff, that's a topological property. If x has some topological property, like being Hausdorff, then, and y does not have that topological property, then we know that they're not homeomorphic. If they were homeomorphic, then they both have to have the property. The same way that in order for me to show that this triangle is not congruent to this triangle, all I need to do, well, no, that's not quite true. That's not a good example. Forget last name. But that's what homeomorphisms do. They maintain topological properties. So if I can show that one topological space has a topological property, and another topological space does not have that topological property, I don't even need to waste my time looking for a homeomorphism, because I already know that they're not homeomorphic. So we're going to prove that if x and y are homeomorphic, and x is Hausdorff, then y has to be Hausdorff, right? Because that is a topological property. But then, what does this proof mean? Assume that it's true for a second. If I want to show that two random topologies, call them A and B, are not homeomorphic, one way I could do that is show, look, this one is Hausdorff, and this one is not Hausdorff. Therefore, no homeomorphism between them exists. Because if it did, then this theorem tells me that this one would also be Hausdorff.
Okay.
And you can do that for any topological property. And that is what we mean by topological property.
You're gonna beat me up, but what does Hausdorff mean again?
We'll get to Hausdorff in a second, that's fine.
Okay.
But I want you to follow this idea of what a topological property is. And just stick with that for a second. If you're confused by Hausdorff, we'll recapture it. But what we mean by a topological property is that it is a homeomorphism maintains that property. That property, when you apply homeomorphisms to some topological space, it still has that property. And one of the big open questions in topology is, so in showing that two things are, let's go back to the case where I'm trying to show that this is homeomorphic to this. And maybe I can't find a function from A to B, but I'm trying to show that this is homeomorphic to this. You might think, okay, here's another way that we can do it. We can check all this thing's topological properties, see if it has them all, see if these basically always have the exact same topological properties. And then if these two things do have the same topological properties, then they are homeomorphic, right? Does that make sense?
Yeah.
That's one of the big open questions in topology right now, is does such a list exist? Right now we know of no list of topological properties such that if two topological spaces have those same properties, then they are homeomorphic.
Why can't we just see if they have a bijection? See if
That's
they-
checking if they have a, that's checking if you can find a homeomorphism between them. That's not a topological property that they inherently have as a topology. A topological property is something I can check on X, or something I can check on Y. A function between two topologies isn't a topological property. It's only a property on a topology if it exists inside the topology. I just give you the topology in a vacuum without any function. It has that property.
Why can't they find a finite list? Like, what makes it so that there's more and more?
Why don't we have a list of topological properties such
Yeah.
that you can just check them?
Yeah.
Why does logic work? Who knows? Why can't we find a list? Who knows? Maybe there's inherently no list. Maybe we just haven't thought of it. Maybe there's some deep reason why no such list exists. Math is always surprising like that. Like, if you go back to, I don't know exactly what year, but roughly 1900, one of the math problems that you would have gotten $1 million for solving was finding the set of axioms from which you can derive all of mathematics. Right? Nice, simple, should be able to do it, no problem. Turns out it was proven that no such set of axioms exists.
Right.
So sometimes the natural way that you think about going to do it comes back to bite you, and nope, turns out that doesn't really work like you thought. So who knows?
Have they proven that you can't find those?
No, it is an open question. Does such a list of topological properties exist? That is an open question in topology right now. So if you can find such a list, you become very, very famous to mathematicians.
No,
Probably isn't very famous the world over. You probably
would I make a headline?
don't know, I don't know, what's the most famous Fermat's last theorem? Does that ring bells? You know, the mathematician proved that. It's like as famous as I can think. Physicists tend to get up there a bit. Everyone knows Hawking. Everyone knows Einstein. Maybe logicians. Gödel. Cauchy. For mathematicians, even Newton was a physicist. Leibniz, there's a pure mathematician. Well, he's also a philosopher. But that's a ways back there. Anyways, let's go over this proof real quick and remind you of Hausdorff. what does it mean for topological space to be Hausdorff? It means if you have 2 points in the topological space, then there exists neighborhoods of those points, or open sets containing those points that don't intersect. Housed off. 2 points are housed off from each other. They have their own neighborhoods. They don't have to share a neighborhood if they don't want. We can find 2 separate neighborhoods for both of them. Housed off. Okay. So, really straightforward proof. And let's just do it. So we have f from x to y is a homeomorphism, and x is Hausdorff. We're proving that y is Hausdorff. Right? How do we prove that? I need to pick 2 points in y and show that I can find open sets containing those points that don't intersect. And you show that's true for any 2 points in y that you choose. So grab 2 random points out of y, f of x, f of y. Good so far? Grab 2 random points out of there that aren't the same point, and we need to show that we can find open sets containing those points that don't intersect. Well, since f of x and f of y are in y and not equal to each other, then there must be points x, y, and x that aren't equal to each other, because f is a bijection, and it's 1 to 1. Or, no, it's just bijection, that's all I need to say. Right? So these 2 points aren't equal to each other, and these are 2 points in x. What do we know about x? It's Hausdorff. So since I have 2 different points in x, then there exists 2 open sets in x, 2 things in the topology on x, is what I'm saying there. 2 open sets in x, such that x is in u, y is in v, and u and v have no intersection. When you intersect them, you get the empty set. They have no points in common. Good? Now look at the image of those. Well, first of all, obviously, if x is in u, f of x is in f of u. If y is in v, then f of y is in f of v. And if u doesn't intersect v, then f of u doesn't intersect f of v, because it's bijection. I couldn't have these completely separate, not having points in common, but then have them map points to the same point. Otherwise, it wouldn't be a bijection.
Right.
Right?
Yep.
Therefore, y is Hausdorff. Good? Okay. That's it.